introduction again for everyone else. Thank you for coming. So this is the first ever installment of the qBraid seminar series. Super excited to have everyone here and for qBraid to be sponsoring these types of events going forward. So without further ado, our first seminar is going to be given by Kanav Setia. He's a CEO, founder of qBraid, and also former IBM Q researcher. So I'll let you take it away, Kanav. Thanks for coming.
Yeah, thanks, man. So this, I'm planning to have this as a very interactive session. So feel free to interrupt me at any time and ask me questions. There you go. So today, I'd like to talk a little bit about quantum simulation to give you a little bit historical context as to where the field of quantum mechanics or quantum simulation comes from, what was the motivation behind it, and how quantum computers could make it faster, or why did even people think of using quantum computers for quantum simulation? Okay, so any story in the world of quantum mechanics starts with Schrodinger and with his equation. So in the year 1926, Schrodinger proposed the wave equation for time-independent systems. Now, people who are a little bit familiar with quantum mechanics, you perhaps have already seen this equation. People who are not familiar, in quantum mechanics, rather than having a state of a particle given by the position and momentum, you specify this function called wave function, which tells you the probability of finding the particle. So the wave function evolves according to Schrodinger's equation. So just the same way in Newton's equation, you can specify the position and velocity. Newton's laws tells you how the position and velocity of the particle is going to change with respect to time. In quantum mechanics, you specify a wave function associated with a particle, and Schrodinger's equations tells you how it's going to evolve or change with time. And through wave function, you can calculate the probability of finding the particle in a given position. Okay, and wave function evolves according to the Hamiltonian. Now, the Hamiltonian is kind of an energy operator. It provides sort of like a landscape. Sorry, is there a question? Whoops.
I think you were asked if you could repeat that last part, if I heard you correctly.
Yeah, sure. So the Hamiltonian gives you a landscape under which the wave function evolves, right? This is a Hamiltonian operator. Okay, and then once you have the Schrodinger's equation, which tells you how quantum mechanical objects behave, then you can start asking, okay, how does it affect chemistry? What can you do with it? Well, turns out you can understand the electronic structure and molecular dynamics of chemical systems using Schrodinger's equations. So essentially, you can predict how two chemicals are going to react with each other, or molecules, and you can predict various properties using Schrodinger's equation. Okay. And then what goes into that equation? How does it expand? Well, so you start with a physical molecule. This, as I showed you on the previous screen, is the Schrodinger's equation. This H is the energy operator, which basically governs this energy landscape, which tells you how the wave function is going to evolve. So the H, which is the energy operator, is a combination of the kinetic energy, potential energy, and Coulombic repulsion. So the way you model your atom or molecule, you argue that the nuclei are going to be more or less fixed. And what you are interested in studying in quantum chemistry is the motion of electrons. Okay, and this is what this equation describes. So you have kinetic energy of the electrons minus the potential energy and plus the Coulombic repulsion. So the electron, they both carry, electrons carry negative charge. And from your high school physics, you may remember that two electrons repel each other. Okay, so this is the equation that you want to solve in order to understand the structure of any molecule. And understandably, this is very hard. The only system for which we know how to solve it analytically is the hydrogen atom. Okay, and that was, I think, solved by Schrodinger himself. And as you can imagine, if you introduce two or more particles, the equations get much more complex, and the analytical solutions are not only are almost impossible to come by, right? And helium atom and beyond, what ends up happening is you have a lot of interaction between electron and electrons, which makes it impossible to come up with an analytical solution for the wave function, or for the many-body wave function. Okay, and since then, what people have done in the past 60 to 70 years is that they have come up with approximate analytical methods to find the ground state energy of helium and other systems. And so these approximate methods, you can imagine, they are sort of ad hoc, where they work based on how good the approximation is. And so there's always a trade-off as to how good the approximation is compared to how well these methods work. Sometimes approximations could be very crude, in which case you get bad results. Sometimes approximations are very good, in which case you get good results, but then it could be really expensive to calculate, right? And so this was the place we were at. We had the beginning of Schrodinger's equation. We have the equation. We know how the system behaves. And then we start exploring, okay, let's study atoms and molecules, and which turns out to be very difficult. And Paul Dirac was the first person to realize that. And in one of his papers, he wrote, "The underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. And the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble." Right? So he was the first one to say, you know what, we figured out Schrodinger's equation. We know how subatomic particles behave, but the only problem is when you write down these equations, they're a mess. We don't know how to solve it, right? And since then, after that part, what people have been trying to do over the last 70 or 80 years now is, with the advent of computers as well, they started developing plethora of numerical methods which are aimed at understanding the electronic structure of molecules, right? These are methods like ab initio, methods, density functional methods, semi-empirical methods, molecular mechanics, etc. And all of these methods work with varying degree of accuracy. So the compute resources which are required, they scale with the accuracy of the end results, right? So if you require more accuracy, then the compute resources which are required, they go up. I'm sorry, there's someone.
If can you repeat the question?
Was there a question?
Maybe not.
Okay.
I think we're good.
So let's keep going. So based on the accuracy required, you end up requiring way too much compute resources. Yep. And then this is where this is where Feynman himself suggested that one of his famous quotes is, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look very easy." So he was the first one to propose, you know what? He said, the reason you're having this problem where you end up requiring exponential resources is because there's those rules that govern the nature are quantum mechanical. So in quantum mechanics, when you put together two or more particles, the resources required even to represent the state of the particle, they grow exponentially, right? And this is where he proposed that this is basically coming from the fact that those things are quantum mechanical in nature. Maybe you can construct this system, which is quantum mechanical in nature, and then perhaps you would have a controllable quantum mechanical system. You will be able to map your system that you want to study to this controllable system, and then maybe create similar situation as your molecule or similar environment, and then study the system that you want to study. So this was a very vague idea. I think it was at a conference in 1981. He just threw it out there. And this idea, someone named by David Deutsche took it and put it on a little bit more literal sense, where he showed that you can actually build a universal quantum computer. So you can define a two-state quantum mechanical system, and you can define certain operations associated with that system. And then you can show that any computation that could be done by your normal computer could be done by this machine. And this was the idea for basically, if you guys are familiar with the idea of Turing machines, then he showed that the quantum computer he described were Turing complete, meaning that anything that could be done by traditional computers, traditional model of computation, you could do with quantum computers. But then he went one step ahead, where he showed an algorithm which ended up getting named after him, Deutsch's algorithm, where he showed that there's something that you could do with quantum computer, which is not possible with your traditional computers. Okay, so this was one of the foundational moments where after that there was much more interest in the field. Now that there was the theory was a little bit on the firmer ground, people started looking into it, and then since then there's been more formal definitions of what the equivalent of a bit is. If you read David Deutsch's paper, then you would see there's still not a concept of qubit or quantum gates. What he described in his paper was a more abstract model. Qubit, even the word qubit came much later, I think sometime in 90s, right? And now let's move on to a little bit overview of the quantum computing. So far, what we've understood is the field sort of like got started with Schrodinger's equation in 1926. People started figuring out the structure of molecules and atoms at a microscopic level using Schrodinger's equations, then realized that the equations, they are really hard to solve. And if you try to solve them computationally, the computational resources required scale exponentially. And this is where Feynman proposed that, hey, maybe you could build a controllable quantum system, which you can then use to study the system you want to study. Before I move on with qubits and a review of the quantum mechanics, I want to quickly check if anyone has any questions.
Don't see anything in the chat either. So yeah, if you have anything going through, feel free to either just unmute yourself or throw it in the chat and I can read it out for you.
Okay, very cool. So moving on to qubits. Qubits are a fundamental unit of quantum information. They are a quantum analog of the concept of bit. So bits could be 0 and 1. Qubits could be 0 and 1 at the same time. The general state is given by alpha 0 plus beta 0. Your alpha comma beta is said to be the wave function of the qubit, and general state of the qubit. So the general state of the qubit is a two-dimensional state that lives in a two-dimensional complex Hilbert space. A lot of jargon, you don't need to know that much. Even if you understand it's a quantum analog of a bit, that is good enough. And then compared to the classical bit, as I mentioned, it could be 0 and 1 at the same time. But what's fascinating is the behavior when you move on to multiple bits or multiple qubits. So the property of superposition, which enables a qubit to be in 0 and 1, to be in the state 0 and 1 at the same time, the same property applies even when you're considering states of 3 qubits or more. So you would have, let's say 3 qubits. So then the possible states in 3 bits, for example, are 0, 0, 0, 0, 1, 1, 0, 1, 0, and so on. So there are 8 combinations. According to quantum superposition, you can have a state where you have a superposition of 0, 0, 0 and plus 1, 1, 1. So that means those 3 qubits are in the state 0, 0, 0 and 1, 1, 1 at the same time. And this is a very fascinating property. And this is sort of the reason why you get this exponential explosion, where you have the number of amplitudes or parameters that you need to keep track of in order to perfectly describe the state of a quantum system, they explode. Okay. Then that was a brief introduction to the world of quantum. I hope some of you are familiar with quantum computing. And this is where you start with qubits, you define your gates, and the same way you have the whole infrastructure in the classical world, you have your quantum bits, qubits, quantum gates, with which you can build out circuits and build out algorithms. Okay, and then the question is, how does quantum simulation happen? At some point, you will need to figure out to map that Schrodinger equation to your qubits, right? And this fuzzy atom, like this differential equation, how do you map that to something which is discrete? Okay, so this is what we'll be discussing in the rest of the talk. So you start with physical molecule. As I mentioned, you write down the Schrodinger's equation. On classical computers, you have exponential scaling, where resources required are exponential in nature, which is why it's really hard to do. On quantum, there are two types of simulations that you can do. One is analog quantum simulation. The next one is digital quantum simulation. So analog quantum simulation is where it is similar to the idea that I described by Feynman, where you have this controllable quantum system which is governed by similar equations to the exact system you want to study. So that's the place where you somehow map the systems and parameters, their scaled down version, and you study the system. So this is something that we will not be discussing today. And then you have something called digital quantum simulation. And this combines the idea that Feynman proposed along with David Deutsch's universal quantum computation, where with universal quantum computation, you define your qubits, and then you have your, I shouldn't say universal quantum computation, gate model. In the digital quantum simulation, you have the gate model, which means your most, fundamental unit of information is a qubit. And then you have quantum gates that you can apply on your qubits in order to do any calculation that you like. And this is very similar to the classical digital computation model that we're familiar with. So then the only thing that's left is to figure out how do we start from these partial differential equations and then go to mapping those to qubits. And before I do that, again, do we have any questions? And how are we doing on the time, Graham?
We are doing good on time.
Oh, perfect. So yeah, please feel free to send me questions if you have any. So you start from your partial differential equations, and then you discretize them. And if you're a little bit familiar then with the world of quantum mechanics, then you know these electrons are fermions, which means these are indistinguishable particles, which are very different from your qubits. The main takeaway here being that electrons are very different from qubits, right? So there's a procedure to go from the partial differential equations that I showed you and converting them into algebraic equations. Once you do that, you have discretized the system, but still it is not ready to be mapped to qubits. Or rather I should say it cannot be directly mapped. So you need some sort of a mapping, which is where you have something called fermion to qubit mapping. And there are many mappings here that you can use. In the literature, one of them is Jordan-Wigner, binary, and Bravi-Kitab superfast, and so on. And so what these mappings allow you to do is to go from your algebraic equations for fermions, or think of it as electrons, to qubits. once you've done that, then what you want to do is figure out an algorithm that you would use to read out the properties of the system that you're interested in. Okay, and there are many algorithms for that. In quantum computation, you may have heard of algorithms such as phase estimation algorithm, iterative phase estimation algorithm, and VQE. I'll present the phase estimation algorithm and VQE in the next slides, and talk about how they are used to read out properties of for the quantum mechanical system that you want to study, right? And so, as I mentioned, there are two main candidates: phase estimation algorithm and the variational quantum Eigensolver. So let's move forward. Now, the problem for quantum simulation, if you go back to the Schrodingers equation, there was this Hamiltonian that I mentioned. One of the things that quantum chemists really like to understand is the ground state energy of the Hamiltonian, or the eigenstates of the Hamiltonian. So what that means is it basically tells you what is the lowest energy of the quantum mechanical system, and what is the next level, and what is the next level. So what are the various energy levels that are possible for that quantum mechanical system? So with this information, quantum chemists can figure out a lot of the properties of a given material or a chemical, right? So phase estimation algorithm, what that allows you to do is, given a unitary operator, think of it as a quantum mechanical operator acting on a state, given that, and given an approximate wave function, you can figure out the eigenstate of that corresponding to that wave function. So what essentially allows us to do is, if I have this unitary, and we can construct that unitary using this function called exponential of minus IHT, which is a function of Hamiltonian. And when you act on the wave function, you'll be able to read out the eigen value corresponding to this eigenstate, right? And one main thing I'd like to emphasize, this could be an approximate wave function. This doesn't need to be an exact wave function, right? And then you can use this phase estimation algorithm for your quantum chemistry problems to figure out the energy, right? And then you have the variational quantum Eigensolver. One of the main downsides of phase estimation algorithm is that this unitary that I showed, it requires a lot of gates. The gate depth, or the amount of gates that you will have to execute in order to figure out the energy, that is huge, right? And this is where you have another algorithm called variational quantum Eigensolver, where what it allows you to do is, if you have the Hamiltonian, which is a summation of terms, then it lets you figure out the average value of each term separately with a much smaller circuit. So the way this algorithm works is, you start with a parametrized ansatz function. Ansatz is a fancy way of saying a guess. So you start with a guess wave function, which is parameterized. So you have these control knobs for your wave function, and you keep tweaking them until you find the lowest energy. Okay, and so this is where this algorithm is a hybrid algorithm where there's a quantum part to it, and then there's a classical part to it. Those knobs that I mentioned, they are governed by this classical optimizer, which takes it through, which gets you this new guess wave function with every value that you calculate, and tells you how you should turn your knobs in order to get to the minimum eigenvalue. Right. So this is a broad overview of VQE, phase estimation algorithm. Now, I understand a lot of this might not have made sense on the most technical level, but here the big takeaways are you started from Schrodinger's equation, which governed your quantum mechanical world. You found out that those equations are really hard to solve analytically. You developed approximate or numerical methods. By numerical methods, what I mean is something you can solve in a computer. And then you found out, okay, even in normal computers, it takes forever to calculate the answer accurately. And that's where Feynman proposed, maybe there's a way to use quantum computers. Quantum computers get developed, and we have now two or more, or many quantum algorithms that you can use to study the properties of quantum system. Right, so I'll be demonstrating this VQE and how you can do it from qBraid account. So if you'd like to try it out, just go and sign up on qBraid.com, make an account, and you should be able to run your first quantum chemistry calculations using VQE. And most of the code you should be able to make sense of what is happening, even if it is hard to make sense of what is going on behind the scenes and how each and every step is getting executed. So at an abstract level, what you start with is importing all the necessary components that you would need in order to set up your problem. And when you set up your problem, you're literally saying that I want hydrogen atom, another hydrogen atom. For the first hydrogen atom, these are my coordinates. So you say that my first hydrogen atom is at 0, 0, 0, and my second hydrogen atom is at 0, 0, 0.735. So this is in angstrom, and you can see that I specify the units. And then I specify something called basis, which is STO3G. Remember when I mentioned that you need to discretize those partial differential equations? That's how you do it. Think of it as abstractly. Then what you do is you define your problem. This sort of initializes the system. Then here, it's a second step where you take the output of the calculation that you just ran, you convert it into second quantized operator, which are a step before you could map it to the qubits. So now these are the things you can now map to the qubits. So then you define the number of particles. For hydrogen molecule, there are going to be 2 electrons. And also this problem is also encoded from the way you defined it here. So it figures out how many particles there are in the system. So let me activate my qBraid environment. And you can just click Shift Enter. This part runs. And then, as I mentioned in VQE, you need a classical optimizer, a classical algorithm, which tells you how to update your parameters for getting the lowest energy. So this is where I import a classical optimizer, and I import parity mapper, which is a way to map from your fermionic Hamiltonian to qubit. So it's a way to map your electronic system to the qubits, right? And then with these two things, you get your parity mapper, and then you convert from your fermionic problem to the qubits. So you get your qubit operators. And if you want to see how your qubit operator looks, you can actually, this should work. Yeah, you can see that these are your qubit operators, II, ZI, yeah. And then if you remember, I mentioned there was a guess wave function involved in VQE. And this is the code for setting up that guess wave function. Okay, and you run this, it goes through, and then finally, because we don't have a quantum computer available online yet, or rather I should say, we can just do a simulation right now. Then you define a simulator backend, and then you can run your calculation and get the energy. So if you run it, then you can see that the ground state energy is minus 1.857275 and so on. It also calculates a few other things like dipole moments, things which are of interest to quantum chemists. Yeah, so that was my talk. I will be happy to take any questions regarding the code or quantum simulations. If people are interested, I can also talk about the future directions or where there are still open questions for research. So if you decide to take up the field of quantum simulation, what are the different directions you can go in where you may end up getting some interesting results that you can publish?